Let's start. Welcome to our bright and early Combinatorics class. So I think 8:30 is a good time to have the class when we're all still awake, and usually we're at our sharpest in the morning like this. So, and this class does require some level of cleverness, so 8:30 in the morning might be the optimal time, but we will see. I'm going to pass out the syllabus to you. This is also online, and the version that's online, I'll try to update that as necessary, but I think the only updates really that are required are what the time of the date and well, the time is going to be 8:30, but the date of the final exam, I didn't know that when I was making out the syllabus, but the final exam schedule may be posted now. We'll talk about this syllabus a little bit in just a second here. As you can see, I am trying to record the lectures, so that's so I can post them after class, and so because there's probably a class in here right after us, that's going to make things a little bit awkward in terms of taping, but we'll see how it goes. And then the notes and the lecture videos, which are really just the notes and me talking over the notes, will be available. We'll post that on the class backboard page, within a day or so of the class. So that's just a convenience for you. If you want to review something that we talked about in class, you can find that portion of the lecture. I don't really expect you to watch the whole thing again, all hour and 15 minutes of lecture, some of which will be, chunks of time where we're doing activities in class, so that'll be sort of just dead air anyway. But if there are specific parts that you want to review, you can find those. And then if you miss a class, which I hope that you won't miss too many classes, but if you do miss a class, you can find, you can look at the lecture video if you miss the class. So because I'm taping, all of the notes will be, I'm writing them on the laptop, so they'll all be projected there. So that's why we're kind of really dependent on the screen, because we won't be using the whiteboard all that often. And then those notes also will be posted in addition to the videos. That's going to be on the Blackboard page, so I'll show you where that is in just a second. Anyway, this is just the first page of the syllabus, right, with just basic information of what the class is. So I assume everyone got to the right spot, right? And of course, our meeting times, and kind of important there are my office hours, which will be in the afternoon on Mondays and Wednesdays, because I have another class from 1 to 2:45, and then so from 3 to 4, and then Tuesdays and Thursdays, though I don't have class, so in the morning I should be in my office, but you can find me other times as well, right? There's how you can email me, and there's my office number, there's my phone number. So email is really it's going to be the most effective way to communicate with me. I didn't turn it off, but do not message me in Blackboard, okay? Do not message me in Blackboard, because I don't get a notification in my email when I get a message in Blackboard, so the message can be languishing there for a long time before I notice it. Okay, so try to email me directly if you need to email me, or you can just call me or come by the office. It's not that far from here, right? If you need to. So I want to mention there a little bit about what the course is all about, and this is going to become really important today. Not important, but really apparent today. Some of the things here that I mentioned in this little paragraph about what the course is about. So combinatorics is kind of a, and that's not a word we use frequently, right? Okay, in everyday conversation. So the whole that topic might be new to you and what that means, but it's actually very elementary aspect of mathematics. Okay, and so combinatorics concerns itself with the study of finite sets, right? So not infinite like in calculus, but finite sets, okay? And that seems like a very easy thing to study, right? So it doesn't look like there's really much to talk about in terms of finite sets, because you've been studying finite sets from your very earliest encounter with mathematics, okay? Because one of the first things that you learn to do as either a first grade student or a preschool student probably even, was you learned how to count finite sets, right? That was one of the first things you learned to do on Sesame Street, right? Or whatever, right? Or in preschool or in first grade, you learn to count. So you spend a lot of time doing that, okay? And that's what we're going to do as well, okay? So we're going to revisit that problem of counting finite sets, which you sort of have probably not thought about much since first or second grade, right? Well, probably the beginning of first grade, right? Okay, the first a few weeks of first grade is when you learn to count, and probably haven't given it much thought since then, okay? Especially counting finite sets. But that turns out to be a much more challenging problem than it seems in first grade. Might have seemed challenging in first grade as well, right? Okay, but once you mastered it, it doesn't seem difficult. But it is really can be quite challenging. And so we're going to revisit that problem here. That's really what the course is about, okay? Studying finite sets, and in particular, learning how to count finite sets, although there are going to be other aspects of finite sets that are going to be of interest to us as well. But we're going to spend a lot of the time learning how to count finite sets, okay? But then later on in the course, we'll maybe explore some other problems that are classified as combinatorial type problems that again are related to finite sets, but are not really just classical enumeration or counting of finite sets. Now, what makes counting finite sets challenging in this course is going to be, of course, the nature of the sets, all right? So when you're in first grade, you're used to learning to count very elementary sets, right? Like you may be asked to count the fingers on your hands, right? Or the chairs in a classroom, correct? Okay? And so you learn a process for counting those, okay? But the sets that we'll be dealing with in this class are not going to be so concrete, all right? So in fact, the objects in them, we're not really going to be able to point to them like we can point to the objects in sets that we're counting in the first grade. And so that's what's going to make the counting problem challenging, is we cannot physically see usually the objects that we're trying to count in the set. They really just exist in our imagination according to a set of rules or some sort of description that is used to describe how the objects are constructed, all right? So you'll be told, here's a set of objects, here's how these objects are constructed, how many such objects are there, okay? And so you won't be able to actually physically point to the objects. Your first grade method of counting is not going to work, right? And then, of course, also sometimes the sets are very large, right? Although they are finite, they can be very, very large sets. And, of course, you could not then, point out and count off each number off each item in the set like you would in first grade, because it would take you too long, right? Okay. So because the elements of the sets that we're going to be working with are defined by usually some sort of process or some set of operations, they have some sort of structure to them, or we think of the objects as having a structure to them. And so sometimes the study of combinatorics is called the study of finite structures, all right? Just because the elements and the finite sets have some sort of implied structure to them, okay? You'll see that when we start looking at examples here, okay, right today, all right? And so so in the book, if you read the book, it says, it gives an elaborate definition of combinatorics. We're not going to explore really carefully all aspects of that definition of the topic, but but it says, combinatorics is the study of finite structures. By that it means sets whose elements have some sort of implicit structure to them. Okay. All right, so that's kind of what we're doing. Now, of course, the techniques that we use to count these sets, they're often quite intuitive or quite elementary. So that makes combinatorics sometimes a very attractive subject. Because you don't have to have a lot of preparation to understand the problems in combinatorics. So even bright grade school students can understand the statement of combinatorial problems. They don't need a lot of conceptual machinery to understand what's being asked when a combinatorial problem is stated, right? How many elements are there in this set is a very elementary sort of question, right? Okay, and again, the solutions to these problems sometimes rely on just sort of our intuition and our sort of very native logic, and so they have a puzzle-like quality. The problems often have a puzzle-like quality to them. And so they're often fun for that reason, okay? They're both simple to state but also challenging and really require us to apply our innate logic abilities, right? Our innate mathematical intuition to solve. So it's fun often, okay? But sometimes also frustrating, okay? Because, when you're accessing your logic and your intuition, that requires effort and sometimes it gets frustrating, right? Anyway... So it's not a subject that's going to refer back to, a lot of elaborate theorems from calculus or, I don't know whether subjects you've taken, right? Okay, it's really very basic, very elementary. Now, on the other hand, some of our counting techniques, a little bit later in the course, we are going to learn that we can apply some things that we've learned in calculus to help us, surprisingly, with these counting problems. Okay, so there is a relationship between continuous mathematics, that would be calculus, and or analysis. That's the subject. That's the branch of mathematics that calculus is part of analysis, and then combinatorics, which is a separate branch of mathematics. Other branches of mathematics, big branches of mathematics, would be algebra. Okay, or geometry. All right, those are usually the four key categories of math. So you probably know a lot about geometry or algebra for sure, right? And analysis, because you've all taken multiple semesters of calculus, but this might be your first real introduction to this branch called combinatorics, which does have lots of applications, not just puzzles. It's not just the applications for combinatorics, but also in really almost every field. Okay, but especially fields like theoretical computer science. So for those of you who are computer scientists or interested in computer science, it has lots of applications in theoretical computer science and also in probability and statistics, and that's really kind of where the modern study of combinatorics began. Okay, so it began in the Enlightenment, although counting problems have been posed, since antiquity, right? Since people started counting, but sort of the modern version of combinatorics or combinatorial problems came about in the Enlightenment when people were studying games of chance, okay? Because the gambling was very popular in the Enlightenment, and so of course that involves understanding how to gamble involves probability, and that often relies on counting problems, okay, or solving counting problems, as we'll see. So that's where sort of the modern version of combinatorics comes from. What else did I forgot to mention there in my little description there? I think that's it, right? Okay, so that's what we're going to do in the class, and we're going to start with some today and this week, and I don't know how long it will take us, but we're going to start with some just examples of combinatorial problems. I don't think there's anything really special about these examples other than they just give you an idea of the sorts of problems that we're interested in studying, okay? And then, so once we've got that sort of little taste of how combinatorial problems look, then we'll step back and start learning the real techniques that we're gonna use, right, to solve these problems. Okay, but at first it's just kind of fun here. We're just going to get familiar with different kinds of combinatorial problems. All right, so there is a book. All right, and this is the book. So I probably am not gonna assign reading from the book, okay? But we will be covering the book according to the syllabus and the sections in the book according to the syllabus. And there is a schedule there, right? So we'll try to stick to that schedule. But I've not taught the course before, and the course has not been taught very often. So I'm not sure how realistic this schedule really is, right? Okay, but we're going to start with Chapter 1. Not all the sections from Chapter 1, though, just some of them, and maybe not even the ones I listed now that I think about it. We may not do all of those, okay? And then we'll go on to Chapter 2 and so forth, right? So we will be sort of following the sequence of topics from the book, but not really planning on assigning readings from the book. I'll try to introduce all the ideas here in class, in lecture, in the notes. Now, however, I will extract problems for homework from the book. So we will have homework problems, and these are just going to be written by you on paper, right? And so I've got that first homework assignment ready. I'm going to pass that out, and so the homework does count for a certain percentage of the grade. And then we will have 3 tests. So the homework counts 15%. And then we will have 3 tests that count 60%, so 20% each. And then we have a final exam, which is comprehensive, and that counts the other fourth. However, if you are satisfied with your grade going into the final exam, you do not have to take the final exam. So what I will do is take the average of your 3 midterm tests, and if you are satisfied with that average, you can use that as your final exam score. So you do not have to sit for the final exam, okay? Unless you don't have the grade that you're looking for, right? And then you need to have the final exam to improve your score, okay? So you have that little bit of a bonus here in the class. But we do have 3 midterm tests, so that's a lot. That's why we have that luxury of not taking the final exam if you don't want to, okay? All right, I don't have a due date yet for the first homework assignment, but I'm going to go ahead and pass it out, and we'll maybe mention it when as we're going through the notes here, and some relevant things come up. You'll notice on the first problem is actually a collection of problems. It says do problems 1, 2, 3, 4a, and 5 from Chapter 1 in the text. Those are actually on the back of the assignment. So there's a Xerox of those on the back. Now, I showed you the text, so it's called Introduction to Combinatorics, or Introductory Combinatorics. It's by a guy named Brualdi. This is not a new book, so I think that this book in PDF form is probably widely available for free online, I think. Okay, has anybody looked for it? Okay, so I think that if you can find just a relatively recent version of the text, that should suffice, okay? But I think it is. I don't know if it's in the bookstore or not. We requested it, but I don't know if it's in the bookstore. And I don't know how much it costs in the bookstore. So, but there's what it looks like, okay? And there are different editions. This is the 5th edition, so, but even the 5th edition is not that new. So, again, I think it might be, you might be able to find this available, okay? In PDF form Okay, let's see. So there's the book. We mentioned the grading. Notice there's a piece of graph paper on the back of the syllabus. We're going to use that today. So you can take that off if you want to, because we're going to use that. That's not really part of the syllabus. So I mentioned the grading there, right? The only other thing I want to mention here maybe are the classroom expectations. So we will be taking attendance starting, I don't know, next time, or can't start Monday, right, because we're off Monday, but or maybe starting next Wednesday, a week from Wednesday. So we'll be taking attendance each day. You do not want to miss more than 4 classes, so I hope that you don't miss any, but or maybe 1 or 2 at the most, but you don't want to miss more than 4, okay, because that'll put you in violation of the attendance policy. That's kind of harsh now, because if you violate the attendance policy, that means you can get a maximum grade of D in the class, okay, unless you appeal successfully to me. All right, so there is an appeal that you can go through, but try not to miss more than 4. All right, because then it'll get messy. We'll have to go through this appeal, all right, of that. Try not to miss a test, right? So if you miss a test, we're going to have to make that up with the final exam. So you will have to take the final exam in that case for sure. And another thing is try to avoid using your cell phone in class. So I'd like your cell phones to be put away. There may be times where we want to use a cell phone in class, okay, to find things. So that's a possibility, but otherwise, keep those put away, right, so that they're not a distraction to you, and in particular, so they're not a distraction to me, because when I see people using their cell phone in class, I get crazy. Do y'all have questions? We rushed through a lot there really fast. I'm not sure I mentioned my name. My name is Dr. Waller, right? Okay. So, and my office there is South 718, which is not far from here. Okay. So, easy to find each other, I think, especially around this time. Okay. Great. Well, I guess we will start talking then about the notes, and we're going to do some things together here during the notes. So these are not meant to be individual activities. You can talk with your neighbors and your friends, okay, when we get to them. These aren't the homework problems. These are notes. But some of the problems that are in the notes are actually homework problems, okay? So I'll mention those that are really homework problems, all right? At first, I don't know, I haven't taught this before, so we'll see how it goes. But at first, I think it's going to seem like I'm taking what are really straightforward questions, right, and really trying to break them down into even simpler steps or questions. And there's a reason why I'm doing that. So if you're thinking about, well, is he ever going to get to the point? It's obvious what's going on here. Just bear with me, okay? Because I'm trying to lay the groundwork for when we get to, really challenging type problems, right? So we'll be able to break them down in the way that I think is most beneficial to solving them, okay? But maybe my scheme here is completely screwy, so we'll see what happens. Oh, I didn't show you the Blackboard page, so there's not much to the Blackboard page. There's the Blackboard page. So there's one announcement, which I sent to y'all via email last week, so I hope y'all got that. And then there are just some, folders here. But I'm going to try to post the homework in Blackboard because I've got to set up the grade book in Blackboard, right? So instead of just handing you the problems like I did today, I'll try to actually incorporate them into the Blackboard page so that it will be easy to set up the grade book in Blackboard so you'll know what your grade is, right, at any given point, although that's not going to really be very relevant until we have the first test, right? So it'll be a few weeks. And then there are some categories here, right, of things that will become available as we go through the class, like there's where the class notes and videos are going to be posted, right? the syllabus is here. I always give sample tests, so when we get ready for a test, our first test, there'll be a sample test there posted, so you can get a feel for the sorts of questions that will be asked on the test, and then that's where I post the answers to the sample test and also the test answers. Okay, this is my version, so of the Blackboard page, right? So this isn't the student view. So there's some categories here that are, as you see, X'd out, that are just remnants of artifacts from prior semesters that are no longer relevant. We don't have really a tutoring option for this class, right? This is a junior level class, and I don't think there are many people who have taken this class who are on campus. So you're going to be depending on me a lot and on yourselves, okay, right, to prepare for the class. So I really strongly encourage you through the activities that we're going to do here in class, right, just meet your classmates, right, and start, if you can, right, creating study groups, okay, so that you can tutor yourselves, right, work together to learn the material in the class. But you have me always, right, just a few steps away, right, in my office to answer any questions. So please make use of me as well, right? Okay, so I know as juniors, y'all are not going to be shy about coming to instructor's office. Freshmen have a terrible time with that. But you guys shouldn't be intimidated by, I think, by coming and talking to me. All right, so that's what the Blackboard page looks like. Here's what the class notes are going to look like, right? Okay, so people who've had me in class before, it's the usual style, right? Okay, so everything is going to be handwritten there, and then so we'll start filling in these notes, and then they'll get posted right after class. All right, so this first part of the notes is just kind of a repetition of what I already said about combinatorics, right? We're going to study finite sets of objects, right? But these objects, these sets will be more difficult, right, to study than prior finite sets that we've probably looked at because for various reasons, right? And the key reason is the objects in the set are going to be sort of virtual objects. There'll be things that kind of exist in our mind. We could create them in reality, probably, many of them, but that's usually clumsy or cumbersome to do. So we have to really manipulate these objects just in our mind, okay? And so that sometimes is a little bit challenging for students to get used to doing that, okay? But you will eventually. But we can't just completely manipulate the objects in our mind. So we do have to sometimes come up with representations for the objects that we're trying to count in a set. But the representations will not be the same as the physical object, right? Okay, they will simply be paper and pencil representations of the object, and that's what we're going to, or the objects, and that's what we're going to practice a little bit here today is how do we start modeling objects in these sets, okay, if we can't actually construct the objects, all right, because it's just not feasible to do that, all right, and that's really an important step in combinatorics, so we'll actually be concentrating on that a lot, okay. All right, so again, I already mentioned sometimes combinatorics is called the study of finite structures, or sometimes it's called the study of discrete structures, all right, but there's a difference between finite and discrete, okay, all right, so let me just briefly there explain the difference, okay? Although sometimes they're considered synonymous. Technically, there is a difference. Of course, a finite set is a finite set, right? Okay, so it is finite. It's not infinite. Discrete sets, however, can be infinite, all right? So discrete sets can be infinite, but what makes a infinite set discrete is that you can put the elements of the set in a particular order, all right? So if you can order the elements of the set, even if there are infinitely many of them, if you can put them in an order, then that would be a discrete set. By an order, I mean this is the first element, this is the second element, this is the third element, this is the fourth element, right? We can sort of number them off in a particular order, even if there are infinitely many of them, okay? So even if this numbering continues to infinity, right? If you can put the elements of the set in an order, right? Really any order will do. Okay? Sometimes there's kind of a natural order that's clear, but any order will do. Then that would be a discrete set, okay? But a finite set, of course, has a fixed number of elements in it. So finite sets are discrete, okay, but not all discrete sets are finite, okay. So a famous example of a discrete set, which is not a finite set, would be the set of rational numbers, numbers that you can write as fractions. That is a set that you can actually put in a particular order, all right? So you can say there's the first one, there's the second one, there's the third one, and so forth, okay? Even though that's a big set. But the set of real numbers, that's obviously an infinite set, right? But that is not a discrete set. So you cannot write the real numbers in an order where you can say, here's the first one, here's the second one, here's the third one, here's the fourth one, okay? That's not possible to do that, all right? So that's kind of the difference between discrete and finite. But we're almost always going to be dealing with finite, okay? So not really discrete sets, although I guess we'll probably encounter some from time to time, okay? All right. So as I mentioned here, we're going to consider some examples here of some combinatorial type problems, okay? So in this problem, this is a long example. It's got several different problems embedded in the same example. What I'm going to try to do to you is describe some sort of situation, and then based on that context or based on that situation, I'm going to identify a set, okay? Right? And then we want to talk about the set. And in particular, what we really like to do is to count the set, okay? All right, so we want to determine the number of objects in that set, all right? So that's kind of the that's kind of the basic structure of format for almost all the problems that we're going to be thinking about in the class. But we will occasionally veer off into some sort of kind of related problems, all right, okay, that really aren't counting problems, but they just kind of naturally arise when we're, dealing with a particular finite set, all right? Okay. So these problems are all going to have kind of a similar, well, the way I present them, they'll always have kind of a similar format or feel to them. But when you actually see these problems stated in practice, they're not always massaged into this format. You have to sort of yourself figure out, what's the finite set that's really being discussed in this problem, okay, right? To realize how that combinatorial problem relates to, finite sets, right? Or the number of elements in a finite set. Okay, now, I think I skipped over something that I wanted to mention, but I'm not sure that I have. No, I haven't. All right, so let's set up a combinatorial type situation, okay? And you're going to see exactly why it's not feasible often to physically construct the objects in a set that we're talking about. All right. Okay. So we're going to think of a chessboard. All right. And so just an 8x8 chessboard. Okay. So did I get this counted off right? 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, okay, so I drew that the right size. So each block there on the graph paper, is one square on the chessboard. Now, chessboards are a little bit more complicated than this because the squares, right, are usually colored as well, right? So in a checkerboard pattern, okay, and that's practically useful, right, because that helps you understand the board better, right? And but I don't have yet the squares colored, but we are going to color the squares eventually here on the chessboard. All right, so now here's what we're going to do, all right? We're going to take some dominoes, okay, right? And so here I've drawn a domino here positioned on the chessboard, all right? And we're going to assume now our dominoes are just the right size so that they will cover 2 squares of the chessboard, okay? I don't really care about the numbers on the domino. Those not really part of this problem, okay? So you've got this domino, and it covers 2 squares on the chessboard, all right? Now, here's what our goal is. We want to take a collection of dominoes, and we want to cover the entire chessboard, okay? So remember, each domino has to cover 2 squares, though, right? Okay? So you can't break the domino in 2, all right? Each domino must cover 2 adjacent squares on the chessboard, all right? So there's one domino covering these 2 squares. But we want to cover the entire chessboard with dominoes, okay? That is called a perfect cover or a tiling of the chessboard, okay? So that's why the title of this section was Perfect Covers of Chessboards, okay? This problem is related to a famous problem from molecular physics called the dimer problem. So it actually has an application, all right, okay? You can maybe read about the dimer problem. If you Google dimer problem, it'll explain to you it doesn't really explain the problem in terms of chessboards and dominoes, but you can understand from the explanation of the problem how the chessboard and the dominoes come about. Okay. All right. So see, that's our goal, is to take the chessboard, okay, and to cover it with dominoes. All right. Now, so what you're wondering here is, well, what's the finite set that Dr. Waller is describing in this problem? Okay. And it's not the chessboard, okay, and it's not the collection of dominoes, okay, although both of those things are important, all right. It's actually the arrangement of the dominoes in the cover, okay. That is the object that we're interested in, okay. So what is the arrangement of the dominoes on that chessboard so that we cover the entire chessboard, all right? So we cover the entire chessboard. That is the set of objects that we're interested in studying here, okay? So obviously, that's called a tiling or a perfect cover of the chessboard. It's an arrangement of the dominoes, all right? Yes?
So are you talking about the number of perfect covers?
Well, yeah, we'll get to that, okay? So, but the object in the set itself is just a perfect cover. So it's an arrangement of the dominoes, all right? How many dominoes, by the way, are going to be in a perfect cover? 32, right, okay. So, because you got 64 squares on the chessboard, right, each domino has to cover 2. So you have, an arrangement is a collection of 32 dominoes, okay, right, okay. But it's the positioning of the dominoes that makes a difference, all right, okay. Because if you position the dominoes in different ways to cover the squares on the chessboard, you get a different arrangement, all right. And, as you just asked us there, the set we're interested in here is the set of all possible arrangements, okay? So the set of all possible perfect covers. Now, you can see why we're not really going to be making objects in this set, because what do we need to do that? To create an object in this set. You need a chessboard, yeah, and what else? 32 dominoes, right? Okay. All right. See, that's a little bit clumsy. So I didn't bring any chessboards, sadly, or the dominoes necessary to cover the chessboard, right? Okay. So we don't have a physical manifestation, instantiation of a perfect cover in front of us. So we have to merely manipulate these perfect covers in our mind. Okay, right? Okay. And that's what we're going to do. All right. Well, with maybe a little bit of help, okay? All right. Now, again, as I mentioned, the basic problem here that we're going to think about is, how many of these arrangements are there, okay, right? So how many different ways can you arrange 32 different ways, right? Can you arrange dominoes on that chessboard so it will cover the whole chessboard, okay? So that's the set that we're interested in. I'm going to call that set T just to give it a name, okay? So there's my definition of the set, right? Okay? It's the set of all of these tilings. That's where the T comes from. The set of all of these tilings are perfect covers of that set, of that chessboard with the dominoes. Now, I'm hoping that it's kind of intuitively obvious to you that the number of arrangements is finite. Are we agreed with that? Yeah, okay, I think it's just clear because the chessboard only has 64 squares on it, right? We're only working with 32 dominoes, right? So there's got to be a finite number, a limited number, right, of ways that we can rearrange the dominoes to cover all of the squares on the chessboard, correct, right? So that's not an infinitely big set, okay? Definitely finite, but could be rather large, right? Who knows, right? And so our goal is to determine the size of that set. Now, I want to introduce just a little bit of terminology here, okay? We're going to call the size of a set, sometimes we'll just call it the size of the set, or we'll call it the number of objects in the set. The formal name for that is the cardinality of the set, okay? So the number of objects in the set is going to be the cardinality of the set. And we're going to denote that, remember T is a set, right? So we're going to denote that by using absolute value bars, okay, around the set, okay? So if I put T in the absolute value bars, that means the cardinality, but that's just the number of objects in the set, okay? Just the size of the set. And that's what we want to determine. So if you determine that cardinality, that's called counting the set, right? Okay, does that make sense? Or a little bit fancier term is enumerating the set, okay? So evaluating this number, which we think is finite, right? Okay, that's called enumerating the set or counting the set. Now, we didn't actually prove for ourselves that this set is finite, okay? So we do want to take up that question because if it really is finite, which seems, I think, intuitively obvious, right, that it's got to be finite. But if it really is finite, we should be able to prove that. And we will try actually formally proving that sort of intuitively obvious fact, right, that this set is finite, okay? But we'll get to that a little bit later, okay, in proving that this number is not infinite. Okay, this is not an infinitely large set. All right, now, we cannot obviously count the set in the first grade manner, okay, because we cannot physically construct very easily, right, the objects in this set. So when you're counting a set in first grade, right, okay, think about how you do that in first grade, right? Usually you have the set of objects in front of you, right? Or a very close representation for the set of objects in front of you, right? Okay? So when you're doing counting in first grade, you're aided by the fact that you can actually sort of see the set, right? You have a physical version of the set with you, right? So if your teacher asks you count the number of toes on your feet, right? Okay, you can do that by just looking at your feet, right? Okay, or if the teacher asks, oh, count the number of chairs in the classroom, correct? Okay, you're aided by the fact that, oh, I can see the chairs in the classroom, right? Okay, so that turns out to be a very great advantage to you in first grade, okay? And of course, in first grade, right, you're really concentrating on, learning your numbers and so forth, right? Okay, so we don't want to make the sets for first graders, right, unnecessarily complicated because they're already obsessed with, learning the integers, right, learning the counting numbers anyway, okay? That's really kind of the key goal there, right, of counting in first grade, okay? But see, we are working blind, right? Because we cannot really very easily sit down and construct, right, all of these different, or even very many, right, of these perfect covers, correct? Because we don't have the chessboard and we don't have the dominoes, right? Okay, so we're sort of flying blind here. We have to sort of create these objects in our mind and count them just in our mind, right? Okay, and so that's kind of the central problem in the course. How do we do that? How do we do this counting when we can't sort of number off the objects, okay, like you would do it in first grade? All right, well, actually, that being the case, let's take up kind of a simpler version of this question, all right? So instead of obsessing here with exactly how many of these perfect covers there are, let's try to convince ourselves that there's at least one, okay? So maybe this is a bogus question. Maybe there are no perfect covers, right, of the chessboard. So maybe I'm asking you about an empty set, okay? And if that's true, right, then that's great. We know the cardinality is 0, okay, if it's an empty set. So this is the first thing we want to convince ourselves of, is this set, its cardinality is not equal to 0, okay? We're not dealing with a trivial set here, right? Okay, there really are some perfect covers of this set. All right, so on your, so this is pretty easy, right? Okay, for that first question, we just want to show that the cardinality of T is not 0. There, I've given you a chessboard. I made the squares a little bit bigger, okay? So I'm treating you kind of like a first grader here. I made the squares a little bit bigger, so it'd be easier for you to write on with your crayons and stuff. No, I'm teasing you, but so I want to see if using that, you don't even have to draw on it if you don't want to, right? Can you describe for me a perfect cover of that chessboard? Okay, so you don't have to draw the whole thing, all right? If you want to, you can, but you don't have to draw the whole perfect cover. Just looking at the chessboard, right? And if you want to scribble on it, that's for you to scribble on, right? But can you find just one perfect cover for me so we can show that this set is not 0, right? Okay, so can you find one arrangement of the 32 dominoes that's going to cover all of the chessboard? Okay, and you can just maybe verbally describe it if you don't want to draw a picture of it, right? Okay, you might describe how it works there. Okay, all right. So there's your first question. You can talk with your neighbor. Okay, so this is a good chance for you to find out about your neighbors. It's always useful to know who's really smart in the class. Okay, right? So,
Can I get a syllabus, please?
Huh?
Can I get a syllabus?
Oh yeah. Okay. Is there anybody else who needs a syllabus? Yes, I'm hoping that visual aid there is enough to clue you in on how you can do this easily. It's pretty easy to do it. Okay. You don't have to really do much exotic there. You may try explaining your solution to a friend there, whoever's next to you, so that they can understand it, right? Okay, so they believe what you're saying. Sometimes you might have not comprehended the question exactly, and then sometimes when you're trying to explain your solution to a friend, right, then you'll realize, whoops, I didn't understand what was being asked of me. Remember, the square here is this whole thing.
Oh, okay.
Yeah, right. It's 8 by 8. Yeah, I drew the squares a little bit bigger, right, on this version. Okay, did y'all find one? Probably found a bunch, right? Let me scroll back up here to the chessboard. So, my version of the chessboard. All right. So, does someone want to describe what they did? What do you think is maybe the easiest one? Uh-huh. So you just arranged all the dominoes vertically, is that what you're saying? So you have a domino here, and then another one there, and then there, right? All right. So, and then you just keep going, every column the same way? Yeah, okay. So then you have another column here like this, right? And so on and so forth, right? Okay, that's going to do it, right? So you would have 4 dominoes, right, for each column, correct? And then just do that for each of the 8 columns, right? So you're going to use up the 32 dominoes, and I think that indeed that covers the whole board, right? So they're easy. That's a tiling, right? Okay. That's it, right? That's enough for us to convince ourselves, right, that this is not just a bogus question, right? Okay, there are some tilings of this chessboard, right? So that cardinality of t is greater than 0. Who has a different one? Slightly different. Oh, just do it horizontally? Okay. Oh, I see. All right. So, all right. So, how am I I can't change my picture here very easily, right? Okay. So you'd have a domino there, right? Okay. And then another one here, and then like this, right? So you just put 4 dominoes on each row, right? Okay. And then just repeat that all the way down. All right. So there is a question here, though, of are those really different tilings, okay? Because if you change your perspective on the chessboard, that the second tiling will look like the first one, right? Or the first one will look like the second. You see what I'm saying, right? Okay. So if you're looking, say, from top to bottom, right? Okay. well, there's what the vertical tiling looks like, correct? Right? But if you change your perspective to the left-hand side, then that same tiling becomes, that first tiling becomes the same as the second one, right? Because you would, if you were looking from this direction, you would think, okay, these are the rows, right? And so I just put 4 dominoes in each row rather than each column. All right. So, so that's something for us to consider, right? Is whether or not those two tilings are really the same. Okay. Are they really different? Because if you just move the, reorient the chessboard, right? Okay, just shift it 90 degrees. The second and the first tiling will look identical, right? Okay. So how can you get one that's obviously not one of these two? Oh, I see. Okay. So in this corner, right, okay, if we were doing the rows, right, if we were tiling the rows with dominoes, then we could take these two and just flip them? Oh, I see, right. So you could have two that over here that are going vertically, correct? Okay. Now that would definitely be different, right, okay, than either one of those first two tilings that we mentioned. I think for our purposes, we're going to think of the chessboard as having a particular orientation. All right, so so we would think of the first two tilings that were mentioned as being different. Okay, all right, so we're going to think of the chessboard as having a distinct bottom here. Here would be a top, there would be a left, and there would be the right. Okay, and those won't change when you rotate the chessboard. So I would say the first two tilings, for our purposes, are different. Okay, but this one is definitely different from those two. Ooh, all right, so well, not only did we show there then that t is not equal to 0, right, but I think we also showed there that t was greater than 2, right? We found 3 distinct tilings there for that chessboard. Actually, now, the correct number of tilings is not a number that's easy to compute, okay? So counting this finite set is not trivial, all right? But the number was determined in 1961, okay? Not until 1961 to be that value that's given there, 12,988,816. So it's a huge number, all right, okay? There are a lot of different ways of arranging those dominoes to cover that set, okay? So a giant number. And that's why it wasn't really hard to find 2 or 3 of them, okay? Because there are actually a lot of them, all right? So in this problem, finding a tiling is not hard, right? But counting them really turns out to be extremely difficult, okay? This result is credited to Fisher, but I think there are actually 2 or 3 other people who answered the question simultaneously. There were sort of 3 solutions to this problem given all at the same time, okay? Or roughly all at the same time. Let's look at a slightly different version of the problem now. So we're going to change the chessboard a little bit, okay? So this is a common thing in combinatorics, right, to just slightly change the problem, okay, and then ask the same or related questions in that slightly different setting, okay? So let's look at a little bit a different chessboard now. We're going to think about a general chessboard that can have, instead of 8 rows and 8 columns, can have any number of rows and any number of columns, okay? So we'll let m be the number of rows, and we'll let n be the number of columns, okay? All right, of course, both those numbers have to be bigger than 1. You have to have at least 1 row and at least 1 column, right? Or otherwise you're not going to have a chessboard at all. All right, so let's look at the case where we have 5 rows and 5 columns. And again, we want to think about the tilings of that chessboard, okay? So 5 rows and 5 columns, but again with dominoes, all right? Again with dominoes. So dominoes have 2 squares, right? Okay, to them. So that's the second chessboard that I put on your in your notes there. I mean, on your activity paper there. There's a 5 by 5 chessboard. Okay, and so again, we're going to use the same name for the set. We're going to call that T for tilings there. But now what I want you to do is to see if you can convince yourself and me, okay, or convince a friend of yours, all right, and me that, well, yourself first, I guess, but then maybe a friend also as a guinea pig there. Now I think that T is empty, right? So there are no tilings of a 5x5 chessboard, okay? So can you explain why that is the case, all right? So when we just change the rows and columns to 5 rather than 8, we end up with no possible tilings at all, okay? So we don't have 12 million, we have 0, okay, in that case, all right? So why is that true? So, well, just take a few minutes there, all right? So I want everybody to think about it, okay? And write something down, all right, Eduardo? So you doesn't have to be a, perfectly formulated paragraph, right? Just write the essence of why you think there are no tilings there, okay? You can experiment a little bit and try to put in a tiling and see what's going wrong, right? Okay? And that may give you a hint as to why T here is 0. Okay, let's see if we can get a coherent answer to this. All right, so if we have a 5x5 chessboard, why is that set of tiling 0? We have a volunteer. Okay, so why don't you come up here and say up here what you were going to say from your seat, okay? You want to show what you wrote?
I can.
You don't have to, but it's up to you. We can switch to the dot cam, that's why. Is it working?
Sometimes it takes a second or two.
Come on. Maybe I'll have to physically turn it on. It's making a sound. It's flashing. Yeah, you do. Wow. All right, you're gonna blind me on an exam.
I write bigger on exams.
No, okay, all right. Well, okay, that's progress. If a var is the name of this stock cam. All right. Okay, there we go.
It's way down here.
Wow. Okay. Let's see. How do I, let's zoom in some. All right, so, just, you don't have to read that back, but just tell us what you're thinking.
So, we can take the squares of chessboard to be a unit of measurement. So we have a 5 by 5 area, which is 25 units squared. And we know that the area of an individual domino is 2 units squared.
Mm-hmm.
And to have a perfect cover, we need to be able to divide the area and get a whole number. But 25 divided by 2 is not. So we can't get a perfect cover.
Okay, so I want to reinterpret what you said. So there are 25 squares in a 5 by 5, right? Okay, but a domino would cover 2 of those, right? Okay, so if you had 12 dominoes, that would cover 24, but we can't break a domino in 2, right? So the next possible number of dominoes would be 13, but that would cover 26, right? So we would have some domino hanging off of the chessboard, correct? Right? Okay. Exactly right. So there's just no way to get a perfect cover there, right? Because you're going to come up with either an extra square that's uncovered or some domino that's going outside of the board, right? Okay. Exactly. Is that the logic y'all came up with, right? Okay. So there's just because 5 times 5 is an odd number, right? But each domino covers 2 squares. There's just no way to fit that dominoes into the 25, correct? Okay. All right. Yeah. So see, in that case, you end up there with not 12 million, right? As I mentioned, perfect covers. You don't get any at all. All right. Now, what was your name? Sean. The same problem is not going to occur, however, in this situation, okay? Because we're going to let the number of rows be 3 and the number of columns be 4. So that gives us how many squares? 12, right? Okay. That gives us 12 squares. So it is conceivable, although we would have to demonstrate it, right? It is conceivable that we could cover the 12 squares with 6 dominoes, right? So we have a potential, correct, here of having a perfect cover in the 3 by 4 case, all right? All right, so this is now actually a homework problem, all right? I want you to see if you can count T, all right, when M is 3 and N is 4. Do I have that on the graph paper? I think so, right? So, yeah, so there's a 3 by 4. See if you can figure out all the different tilings in the 3 by 4 case, okay? How many are there? Start with 1, all right, okay? So you've got to have at least 1, correct, right, okay? In the prior case, we had 0, so don't have 1, right? So make sure you have 1, but after you've gotten 1, right, okay, then see if you can come up with all of them. All right, so see if you can convince yourself that you found all possible arrangements, right, of dominoes on that 3 by 4 chessboard, okay? So that's going to require, I think, some experimentation, all right? You may have to be drawing lots of 3 by 4 chessboards there. That's one of your homework problems, though, okay? So that counts as a homework problem. All right. Now, as I mentioned earlier, right, chessboards have this other feature, right, that that the squares are, covered, colored white and black alternately, right? So here I've colored our chessboard, our original chessboard. This was a white square, and this is also turns out to be a white square as well. Okay, so the top left-hand corner and the bottom right-hand corner are both going to be white squares the way I colored this. Okay, now here's another way of slightly altering the problem. Okay, but asking the same question. All right, so what I want to do here now is, and this is very typical in combinatorics, right? We start with some basic problem, and we maybe see if we can find a solution to that, and then we start asking variations on the same problem. All right, so here's what I'm going to do now. I'm going to cut this, so we really cannot replicate this very easily, right? I'm going to cut this square off of the chessboard, and I'm going to cut this square also off of the chessboard, all right? And now I'm going to try to cover that chessboard, all right? So I want a perfect tiling for that. That's called a pruned chessboard, okay? Or sometimes I call it an occluded chessboard, right? Because we can't put a domino here, or we can't put a domino here because that's not really part of the chessboard, all right? So, okay. So that's our question, right? How many tilings do we have of this pruned chessboard? Okay, and we could prune the chessboard in different ways as well. All right, so we could cut out squares in a different pattern, but here I'm just taking a really easy pattern there. Okay, all right. So again, I'm just going to ask the same basic question, right? Okay. How big is that set of perfect tilings? Okay. All right. My claim is this one is empty. So we have 12 million, more than 12 million perfect tilings if the two squares are included on the corners. But if I cut them out of the chessboard, then I'm down to 0 perfect covers. Okay. So that one little change there will eliminate 12 million tilings, okay? All right, so why is that now the case? Now, we can't use, Sean, we cannot use your reasoning here because we have how many squares left?
An even number.
Yeah, we have an even number. So, yeah, we have 64 minus 2 is 62, right? Okay, so we do have an even number of squares, so it's possible, right, that we could fill that up with 31 dominoes, correct? Because we got 62 squares, so 31 dominoes would, at least the counts would be correct there, right? Okay, but I claim that we really cannot do that, okay? So there's no way of getting the 31 arranged here, all right, on this pruned chessboard, okay? All right. Now, what you should really take into account here to help you understand this is the black and the white coloring, all right? So the black and the white coloring really helps with this version of the problem, okay? All right? So I encourage you to take that into account, okay? The black and the white coloring. It's really not necessary for the problem, okay? But for the statement of the problem, but it really helps you in thinking about why t is 0, all right, or why the cardinality of t is 0, okay? All right, so think about that for a minute. We're almost out of time, okay? I'm going to stop my tape here.